Previous video, I have already talked about the general mechanism and the process of mechanochemistry, and in this video, I will be talking about the use of mechanochemistry in the synthesis of various products. First and foremost, I will be talking about metal-mediated and metal-catalyzed reactions. They are a type of reaction in the study of organometallic chemistry. An example of these type of reactions is the cross-coupling reaction. Cross-coupling reactions involve a reaction in which reactants are joined together by a new carbon-carbon bond with a metal catalyst. Examples of such reactions include Kumada coupling, the Heck reaction, Sonogashira coupling, the Geishi coupling, Stereo coupling, and Suzuki coupling. Mechanochemistry can be integrated into the coupling reactions, which uses various organometallic starting materials like organoboron, organozinc, and organotin. There would then be the integration of different catalysts like platinum or palladium containing materials to produce a new carbon-carbon bond. Another carbon-carbon bond forming process that can utilize mechanochemistry is olefin metathesis. The process of olefin metathesis is as shown here. Literature experimental values for mechanochemical ruthenium catalyzed olefin metathesis in the presence of solid auxiliaries and the Hoveda-Grubbs catalyst have shown to produce products of yield ranging from 70% to 93%. As there are relatively high yields of products obtained on average, it shows that mechanochemistry is indeed a very useful method for preparing new alkenes from two separate carbon-carbon double bonds via olefin metathesis. Another carbon-carbon bond forming reaction that can utilize mechanochemistry is the Friedel-Crafts reaction. The Friedel-Crafts reaction is a reaction that attaches either alkyl or acyl substituents onto aromatic rings. The Friedel-Crafts alkylation proceeds by using an alkyl halide as a starting material and a strong Lewis acid as a catalyst, as shown in the picture on the top. On the other hand, the Friedel-Crafts acylation proceeds by using acyl chlorides as a starting material and Lewis acids as a catalyst for the reaction to proceed, as shown in the picture at the bottom. Literature experimental values via mechanochemical activation obtained yields ranging from 34% to 99% with an average of around 70%. As there are certain substituents that indeed showed a yield of 99%, this shows that mechanochemistry can indeed be used in Friedel-Crafts reaction to produce products with high yields. The next reaction that I am going to talk about is the synthesis of alkoxysilanes. Alkoxysilanes can be directly synthesized through mechanochemistry. For the current alkoxysilane synthesis, there are various problems like economic and ecological impacts. There is the production of hydrogen chloride containing waste from the production of silicon polymers from the chlorine containing organosilicon monomers. In addition, the process also utilizes high amount of temperature, which indicates high energy and high monetary usage. Mechanochemistry can directly produce alkoxysilanes using an effect known as the abrasion effect. It provides a developed silicon surface with catalytic centers. The process of producing alkoxysilanes require a long preparation stage before obtaining the starting reactant for the synthesis of the alkoxysilanes, as shown in the picture at the top. The reaction would then proceed as shown in the picture at the bottom. As the usual synthesis produces unwanted products like carbon monoxide, silicon tetrafluoride, and silicon tetrachloride, it is definitely not atom economic, and it does not fulfill the principles of green chemistry. The use of mechanochemistry can allow the reaction to proceed without the use of the precursory steps to produce the starting reagents of the synthesis in the bottom picture. The vibration reactor works with a working chamber and brass grinding bodies, with the main components being copper, which acts as the catalyst in the reaction of silicon with alcohol, and zinc, which can promote this process. Experimental data had shown that indeed without the treatment of the starting silicon material with hydrogen fluoride to remove the tin oxide layer on the surface of silicon, the reaction had still proceeded to form the desired alkoxysilane products with high yields. The catalytic copper had entered the reaction directly from the grinding bodies, therefore there would not be any silicon tetrachloride byproduct formed in the synthesis of the alkoxysilanes. Therefore, this indeed shows that mechanochemistry can be used to make the synthesis of alkoxysilanes greener and more environmentally friendly without the production of harmful byproducts. Last but not least, the last reaction I am going to talk about is the synthesis of ammonia through mechanochemistry. The current widely known synthesis method of creating ammonia is known as the Haber process or the Haber-Bosch process as shown here. The process is an exothermic reaction and it utilizes one equivalent of nitrogen gas mixed with 3 equivalent of hydrogen gas to produce 2 equivalent of ammonia gas. Due to kinetic reasons, the Haber-Bosch process must be conducted under extreme conditions like temperatures of 400 degrees Celsius to 500 degrees Celsius and pressures of above 100 bar. Literature has shown that ammonia can be synthesized at a temperature of 45 degrees Celsius and pressure of only 1 bar with the use of ball milling and iron powder as catalyst. The mechanochemical synthesis of ammonia can be divided into 2 steps, which are the nitrogen dissociation step and the hydrogenation step respectively. For the nitrogen dissociation step, through the collision in ball milling, there are low coordinated defects being formed. Nitrogen is then adsorbed and dissociated into atomic nitrogen on the defects of the nitrogenated ion particles. For the next step, the nitrogenated ion particles are then hydrogenated 1 hydrogen at a time and thereafter detached from the ion surface after mechanochemical energy is supplied. This produces ammonia as the final product. Literature experimental values have produced ammonia with yield of 82.5 volume percent, which is a very high percentage as compared to previous state-of-the-art literature values. In addition, the conditions used in the experiment was only at a temperature of 45 degrees Celsius and a pressure of only 1 bar, which is already much lower than the current industrial practices of normal Haber-Bosch process, which is at temperatures of 400 degrees Celsius to 500 degrees Celsius and pressures of above 100 bar as said before. This shows that mechanochemistry allows the production of ammonia to be conducted at much lower temperatures and pressures which in turn reduces the amount of energy used, making it more energy efficient. This makes the Haber process, which uses mechanochemical synthesis, a better alternative than the current industrial Haber process of producing ammonia. In conclusion, I think that mechanochemistry is indeed a very good method for the synthesis of many compounds without the use of solvent. Since it is also greener in terms of it being atom economic and not releasing any unwanted byproducts, it could possibly and potentially replace many syntheses that require the use of strong heating or solvent to proceed with the reaction, therefore making it more economically and more environmentally friendly to produce industrial products on a large scale. In addition, since mechanochemistry can possibly make reactions undergo synthesis under milder conditions than traditional synthesis, it requires lower energy to proceed, which is also more environmentally friendly. Thank you for listening, and this is a list of references used. Thank you.